Welcome back. In this fifth installment of the simple linear regression series, we'll be focusing on the population regression line slope, beta 1, with the goals of being to find a confidence interval for this slope and estimate it, describe how certain variables are related to the width of that confidence interval, and then perform a hypothesis test for that population regression line slope. So we've looked at slope before, but that was the slope for a sample regression line. So that would be B1 rather than beta 1. So let's just revisit what we learned there. So we had said that we were going to interpret the sample regression line slope as the rate of change, where as x increases by 1 unit, by how much do we predict y will either increase or decrease? So with the gas station example, since X was traffic and Y was sales, we said that, well, for each additional +1 in traffic, now traffic was in thousands of vehicles, so for each 1,000 more vehicles passing by, we expected an increase because their slope was positive, and specifically an increase of 0.237 thousand gallons of gas. So that sample slope is a point estimate for the population slope. All right. So this calculation was made on these 80 specific gas stations that wound up in this one sample. However, if we went and got 80 different gas stations, we'd likely come up with at least a slightly different sample slope. Now, without the ability to go get 80 more gas stations, I can't show you that exactly, but what I thought I'd do is I randomly subdivide the 80 gas stations into 4 samples of 20 each. Right? So these 4 scatter plots each represent 20 of the gas stations, and then I fit a regression line to each one. So notice the sample slope changes, in most cases staying pretty similar. It's like 0.261, 0.264, those are pretty close. But sometimes getting farther away, like in the bottom right, 0.149, that one's pretty far away from the rest. Okay. So we just have to be cognizant that our sample regression line slope is merely an estimate of the true population regression line slope. Hopefully we're close to the true value, but we may or may not be. We can, however, estimate with confidence. So coming up with a confidence interval to try to narrow in on where the true value of the population regression line slope lies. Now, why the emphasis on the slope? Why not so much the intercept? Well, the intercept is a constant in this equation. So, it has some value, but it's just there. Now, the slope, it has a constant value as well, but that's what's getting multiplied by x. So if we increase x, that change gets multiplied by the slope. So it's really the lever by which changes in x relate to changes in the mean y. Okay, so remember, this is our population regression line equation, which models the mean value of y, the true mean value of y at a given x. All right, so if we add one more x, beta 1 is the amount that we expect this mean to change. It's the true mean change in y associated with a 1 unit increase in x. We always think about x increasing because a +1 is a nice constant. We can multiply anything by +1 and it's not going to change the value. All right, so as with other parameters, like say a mean or a proportion, we can do 2 types of inference. We could estimate the value of the parameter using a confidence interval. So that's what we'll do first. And then towards the end of the video, we'll test the parameter using a hypothesis test. Right. Now, I want to remind you that these inferences, jumping from the sample to the population, require that these 5 assumptions are in place. So that was the whole purpose of video 4, was to check if these things were reasonable. So we already went through all 5 of these for the gas stations. I'm not going to do it again here. but just a reminder that that's necessary before, say, constructing a confidence interval or performing the hypothesis test. Okay, so let's think about constructing this confidence interval to estimate the true population regression line slope. All right, now all the confidence intervals this semester have the same basic layout. We'll have a point estimate at the center of the confidence interval, and then we'll go plus or minus a margin of error in both directions, above and below. And that margin of error consists of the product of a critical value times the standard error of the point estimate. Okay, so if we're trying to estimate the population slope, what do you suppose the point estimate would be? I actually mentioned this briefly a couple minutes ago, but we'll see if you were paying attention. Well, if we want to know the population slope, a good place to start would be with the sample slope. So the point estimate is going to be B1, the slope of the sample regression line. Now, how much padding do we need to put on that sample slope? Are we likely to be really close to the true population slope or maybe not so close? For that, we need a critical value, and this is going to be a type of T interval. So it's a T critical value. And then the standard error of this point estimate has a formula that looks like this. So on top, we have the standard deviation of the errors. And on the bottom, the standard deviation of the x values times the square root of n minus 1. So this T critical value, remember T distributions are slightly different widths depending on their degrees of freedom. And in linear regression, the degrees of freedom are going to be n minus 2. Okay. So although we'll have JMP calculate the interval endpoints, I would like you to know the relationship between each of these quantities and the width of the interval. So remember, with estimation, we would like a narrow interval. If the endpoints are close together, then we've really pinpointed where the parameter's true value is likely to lie. If the interval is wider, there's less certainty. We're still the same level confident, but there's more possible values that the parameter could take on. All right, so I'd like to consider each of the variables on this list and what's the relationship between each of them and the width of the interval. Is it a positive relationship? So positive is this thing goes up and the width goes up. Or is it a negative relationship where this thing goes up and the width goes down? Or is there maybe no relationship where you change this thing and the width stays the same? Okay, so you might consider where is the thing located in the formula, or you might just rely on common sense. So pause the video and see if you can reason it out. All right, so the sample slope, B1, does not affect the width because its position here puts it right at the center of the interval. So that decides where the interval is gonna be centered, but it doesn't affect the width at whatever position it's at. Only the things after the plus or minus are involved in the margin of error and affect the width. All right. So the confidence level is going to affect the width the same way that it always does. If we want to be more confident, the interval has to be wider. So a 99% confidence interval would have a larger T critical value, causing the margin of error to get larger, so the whole interval gets larger. All right. Then we move over. We've got the standard deviation of the errors. Now remember, this is the typical amount of error for our estimates. So kind of common sense, hopefully, is not too hard to wrap your mind around that if there's a lot of error in the estimates, there's going to be a lot of fuzziness in trying to estimate the population slope. And then mathematically, well, it's in the numerator. So if this gets larger, this product is going to get larger. On the other hand, we have the standard deviation of the x values in the denominator. So we're dividing by that amount. So as it gets larger, the width gets smaller. So we have a negative relationship there. This is saying that if you want to estimate the true slope, it's helpful to have a wide variety of x values. Kind of common sense that makes sense. If we really want to understand the true relationship between the amount of traffic and the amount of sales, you wouldn't want to go get a bunch of days where the traffic is pretty much the same. You would want a broad spread so that you can see the whole spectrum. All right, lastly, the sample size n, that one, hopefully, just off the top of your head, that as the sample size goes up, the interval width goes down. And that's a function of its position here in the denominator. All right, so let's go to jump. I'm using my gas stations. So we always begin by fitting y by x, and we're still trying to predict sales based on traffic. And we've got to fit the line. All right, so to get the confidence interval for the slope, well, I'll just point out here before we do that. So in our sample regression line equation here, this is the sample slope, 0.237-ish. Okay, so 0.237 is going to be the center of our confidence interval. But the question is, well, how far do we have to go out, plus or minus, from that to be a certain percent sure that we capture the true slope? So we're going to scroll down to the section called parameter estimates and put your cursor somewhere inside the body of that table and right click. And get some options. Go to columns, and we're going to add in the columns for lower and upper 95%. You have to do them one at a time. So right click again, columns. Okay. So this is giving us 95% confidence intervals for the intercept, so that's beta naught, and also the slope. Now it's going to it's not going to say slope. It's going to use it's going to title the slope whatever your x variable was titled. So my x was traffic in thousands of vehicles. So in my parameter estimates table, it's called traffic in thousands of vehicles. But this is the slope. So the estimate of the slope, like we said from the looking at the linear regression equation up above, is about 0.237. The standard error is about 0.024. So that is this whole fraction here. That's the standard error of the sample slope. 0.024 is the value that it works out to be in this case. And then to get the interval endpoints, so if you did this entire calculation, the lower would be if you subtract. So on the low end, we come up with an estimate of 0.188. And on the high end, we have an estimate of 0.285. So we're 95% sure that the true population slope lies between those two numbers. But let's see if we can interpret it just a little bit more. After all, what does the slope tell us about the relationship? Okay, so what exactly can we be 95% confident about? Well, we're sort of going to match together, what's the typical format when we interpret a confidence interval with how did we interpret sample slope? You just turn that sample interpretation into a whole population interpretation. So I wrote, we can be 95% confident that as traffic volume increases by 1,000 vehicles, so that's our +1 for x, the population mean gasoline sales increases by between 0.188 and 0.285 thousand gallons. All right, I was able to say increases because both the lower and the upper are positive. So I'm, quite confident that it's a positive relationship. But more importantly, with the confidence interval, we get a sense of how much. So what's the payoff? For a certain amount of traffic, what change in sales could we predict or expect? And if you're running a gas station, that would be good to know. Comparing two roads where you might be placing your next location, you could see, how much of a payoff you could expect for the difference in traffic between those two locations. All right, so why don't you open up the muscle data set and go ahead and try to find that 95% confidence interval, come up with the sentence of interpretation, and then come back and check, see how you did. All right, so this was a bit of a trick. Oh, let me pause here. I'm going to plug in, and I will be right back. All right, so I was just saying this was a little bit of a trick question. I imagine most of you, those of you who at least tried to do the question, went ahead and right away constructed a confidence interval. But remember that confidence intervals are a form of inference. So really, we should be checking the necessary conditions before finding and interpreting a confidence interval. So let's take a really quick run through that. We want to use age to predict muscle mass. So is it reasonable to assume a linear relationship? Remember, our quick first pass check of this is to look at the scatter plot. Does it seem like it's a mostly linear trend and not any curved pattern? So far, so good. I think it looks pretty linear to me. Then I'm going to fit the line. And using the lower red triangle for linear fit, plot the residuals. And we're going to use the first, third, and fifth plots. Okay, so still checking for a linear relationship. I'm looking at the residual by predicted plot, and I don't spot any obvious curved patterns. It looks like a pretty random scatter. So a linear relationship is reasonable here. Next, is it reasonable to assume constant variance across X? So I'm looking across this plot. Do I spot any funnel shapes? Does it seem to be getting narrower or wider as I go across? Nope, the scatter looks pretty of even thickness across the plot. So constant variance is good here. How about independence? Is it reasonable to assume independent errors? Now, first, I'm going to peek at my data table and verify that it does not appear that these values have been sorted in any way. They're not going from smallest to largest or largest to smallest for either variable. Okay, so they look pretty randomly arranged. So I'm going to go ahead and assume that then the data table is structured in the order of data collection, meaning that my residual by row plot could help me spot any patterns over time, if any, were present. So looking at the plot, it's going up, it's going down, it's going up and down and up. I don't see any consistent trend where it's going, up across the whole thing or down across the whole thing. So independent error seems reasonable here. For normality, I'm going to go down to my residual normal quantile plot. And while not perfect, the points do kind of oscillate back and forth along the straight line. The scatter that's present doesn't go outside of the dashed bounds. So I think normality is a good assumption as well. And then the final assumption is just that we have a random sample of the population. So seeing as all these men were between the ages of 43 and 78, I'm going to limit my inference to men of that age range, because we certainly don't have a representative sample of people of all ages or both sexes. Okay. So with all those things checked out and seeming like reasonable assumptions, then I'm going to feel comfortable going to my parameter estimates table, right click, and adding in the columns for the lower and upper 95%. All right, so although we do get a confidence interval for the population regression line intercept, we're not going to worry about that. I won't ask you to interpret it on a test or anything. We're going to focus on the slope. So here, they're both negative. So we can be pretty sure that the population regression line slope is negative. And how steep is it? Well, we have two numbers that we believe it lies between. So I might say something like, we can be 95% confident that for each additional year of age, the population mean lean muscle mass will decrease by between 0.62 and 1.43 pounds. Okay, so we're estimating how much of a change is there in the mean lean muscle mass associated with a 1-year increase in age. And probably in there I should have qualified that this is for men ages 43 to 78. All right, so the confidence interval for slope allowed us to estimate, the magnitude and the direction of the slope. If instead our focus wasn't on how big was the rate of change, but rather, is there a relationship, then maybe we'd use a hypothesis test for the slope. So this is a type of t-test. It'll be a t-statistic. Okay, so the big question is, does X help predict Y? Right, so the null hypothesis is that no, X does not help predict Y. So there's no predictive linear relationship between them. And if that's the case, then the slope in the population would be 0. Because, as X changes, that change in X would just get multiplied by 0 and disappear. Would not affect Y. All right, for the alternative hypothesis, we're going to hypothesize that the slope is somehow different from 0. And we may pick a direction based on what's known about the situation. Now, we really shouldn't be picking a direction based on plotting the data and peeking at it. In theory, we would pick this direction before the data is even collected. Now, just knowing from everyday life what goes on at gas stations, it's pretty common sense to hypothesize that if there's more cars going by, the gas station would sell more gas. Cars are going by. As cars drive, they need more gas. More people will stop and fill up. Okay, so in that case, it would be reasonable to hypothesize a positive slope that, for all gas stations, there's a positive relationship between the amount of traffic and the amount of gasoline sold. So I would pick this one in the middle. There might be cases, though, where we expect that we have two variables that are negatively related. So in that case, we'd pick this third option here. And then maybe there's two variables where you really have no idea. You're just kind of exploring the data. Could potentially go either way. In that case, you would just test that the slope is different from 0. But somehow they're related, but you don't know in which direction. All right, so this is a hypothesis test. So we're going to follow the 7 steps. And if we're using the gas station example, then like I said, we would predict in our alternative hypothesis that there's a positive relationship. We think that there's a general tendency that as traffic goes up, these sales will go up as well. On the other hand, if they're not related, then the true population slope would be 0, indicating that there's no linear relationship between them. Right, step 2, we would state our significance level. based on the risk of a type 1 error, the risk of a type 2 error. In this case, I'll just use 5%. And then step 3 is really where our assumptions would go. Now, we checked these in the previous video, but just to remind you what they were, these 5 things right here. And we are assuming them, but we're assuming them after looking at the data and confirming that there's no obvious problems. So for each of these conditions 1 through 4, you should be citing specific plots and what pattern you saw in the plot that makes you think this is a good assumption. For instance, constant variance. You'd say something like, well, on the residual by predicted plot, there was random scatter of similar thickness across the plot, no funnel shapes. And that would let us know that, yes, it's a good assumption that there's equal or constant variance for this data. All right, so for this t-test, this is what the t-statistic would look like. So remember, our t-statistics are like a signal-to-noise ratio. So what signal is there that the population slope is different from 0? Well, we have a sample slope. Let's use that. So the sample slope is our signal. And then the noise is the typical variability we would see among different sample slopes. So that's the standard error of the sample slope. So we saw that. I'll just refresh, go back a little bit. That's this guy here that was in the confidence interval margin of error. All right, so that's a standard error of the sample slope. All right, so JMP is going to give us this t ratio, but it's just this estimate here in the bottom row divided by the standard error next to it. So in this case, our t statistic is 9.74. So that's what we would write down for step 4. And then right next to it, we're given a p-value, but notice that's prob greater than absolute value of t. So this is two-tailed. This is checking, is there any relationship between the traffic and the sales? We only wanted one tail though. So how do you suppose we're going to go from 2 tails down to 1? So you might have thought, well, let's divide it by 2. So that's correct, provided that you hypothesized in the direction that actually matches the result. So what do I mean by that? Our alternative hypothesis suggested that there was a positive relationship. So greater than 0 would be positive. So I'm going to look at my t ratio. Did I get a positive t ratio? I did. There's no minus sign here. So it's a match. So if there's a match and you had a directional alternative hypothesis, you can, in fact, divide your two-tailed p-value by 2. So our p-value for this gasoline station test is going to be half of this amount. On the other hand, what if for some crazy reason you thought it would be a negative relationship? So you expected negative and you got positive, that would not be a match. So basically, you're completely backwards. So your p-value will be the complement to the one we just calculated. So 1 minus half the two-tailed. Basically saying, hey, you're nowhere near confirming what you hypothesized. You're completely backwards. It's not going to happen very often, but just be aware that you can't always just automatically divide this by 2. Okay, so here, a positive test statistic was in the direction we anticipated. We thought we'd get a result above 0. So everything, checked out according to plan. So we can divide that two-tailed p-value by 2 and say now that it's less than 0.00005. So very small, smaller than alpha. We had picked 5%, so definitely smaller than that. So we can reject the null hypothesis here and support the alternative. So we can be very confident or very certain that the true population slope is positive. So we have strong evidence of a positive predictive linear relationship between traffic volume and gas sales. Which is to say, in other words, we are convinced that as traffic volume increases, gasoline sales tend to increase. Now, that's a tendency for the population. We can't be sure that it's going to work for every single gas station, but the general trend is as one goes up, the other does as well. All right. So for the confidence intervals, only the 95% is built into jump. So I'll just be asking you for those for the slope. Definitely need to know how to interpret it. Be able to state the relationship, like I might say, suppose n increases. For a larger sample size, what would you expect for the width of the confidence interval? And you should be able to say that if n increases, the width goes down. And then lastly, be able to perform these 7 steps of hypothesis testing. You won't be required to calculate the test statistic by hand. JUMP will give that to you. JUMP will give you the two-tailed p-value, and then you'll need to decide whether to leave it as is, divide by 2, or take 1 minus the p-value divided by 2. All right. In our next video, we'll be also doing more inference, but we'll be thinking about what can we say for a fixed value of x.